Hi everyone, so welcome back. So we are looking at space complexity. So we just defined space and non-deterministic space. So space f of n and n space f of n. So we know that they are simply classes of languages and accepted by deterministic Turing machines in space, big O of f of n, or non-deterministic Turing machines in space, big O of f of n. So then we have this two examples. The first one that says SAT is in deterministic linear time. Okay, so it deserves some thinking about this problem. So we know that SAT is NP complete. Okay, let alone that it can be done in, so it's unlikely that it can be solved in polynomial time by deterministic Turing machine, not let alone that in linear time, right? But it is in deterministic linear space. Well, the reason is we have, let's say we have n variables, right? So n variables, so we can enumerate all the truth assignments in linear space, right? One at a time, right? So because you only have n variables, that means that truth assignment, so you set it true is one, you set it false is zero. So you can use a space to enumerate all possible truth assignments. Then for each truth assignment, you evaluate the variable. You evaluate the formula using de Morgan's law. So that will not take more than the space of the length of the formula itself. Hence, it is deterministic because we can just enumerate all possible truth assignments. And for each truth assignment, we evaluate the formula using de Morgan's law. So then that's deterministic linear space. Okay, so now we see that the space complexity is a different beast, right? So it's much different from deterministic versus non-deterministic time. So space is different. It's a different beast. The next example says the complement of or NFA, okay, so which is a set of all descriptions of NFA, and A here is NFA such that such that the language accepted by A is sigma star. So the complement of this let's see. The complement of this, that means L of A is not sigma star. That means that there are some strings that is not accepted by A. So it's non-deterministic, just means that from one state to the other, or from one state you have different choices to go to the other state. But once you read the description of NFA, you just need to check to see whether there are some strings that are not accepted. Okay, so that can be done in linear space. Okay, so, but since this is a non-deterministic time, so we have to guess a path, right? So we guess a path and see. So, and that path will not be longer than the number of states. Okay, so hence that's linear and is not deterministic. All right, so that's some examples. So here I have a note here that we don't know whether this problem is in NP or co-NP. Okay, so that's kind of interesting here now. So this problem, we don't know whether it's NP or co-NP. All right. So the next thing we would like to look at is the relationship between non-deterministic space and deterministic space. So in this particular case, as you can see here, we have that n space of f of n is a subset of deterministic space f square, f of n square. So what that means is that within polynomial, actually within quadratic function, n space is included in deterministic space. So this is much different from deterministic time versus non-deterministic time. We definitely don't have n time of f of n that's included in d time of f of n squared. So that we don't know, but for space we do. And this is called Savage's theorem. Okay, so we're going to devote this second half of the class to look at this theorem. And after that, if we have time left, we may go through a concept of space completeness. Okay, but I hope that we are going to have a good understanding of this proof. Okay, so this is quite interesting by looking at space complexity in this way. Okay, so now what that theorem says is this. For any function f, with f of n greater than or equal to n, because you have to read input, so that means you need at least linear space. All right, but of course, if you separate the input tape from the working tape, then if you measure the working tape, if the space of the working tape, space f of n for the working tape is greater than log n, then we still have this. Okay, but now we just say we are looking at a single tape. The input tape and the working tape is on one tape, so you need to read the input. So that already takes linear space. So that means that we want this f of n greater than or equal to n. So if that is the case, then non-space f of n is included in deterministic space f of n squared. Okay, so let's say how we are going to prove this statement. So we have this naive approach. So what we do is, let's say we try all the branches of the non-deterministic computation. Okay, so we know that non-deterministic computation could have, it's a tree-like structure. So it's this tree, so we start from the initial configuration. And then you may have different possibility to go to the next configuration and go to the next, and so on, right? So then you look at each of these computation. Right? Each of these is a computation. Look at each of these. We know that the space for each branch is at most f of big O of f of n. That's for each branch. Okay, so now try all the branches of the non-deterministic computation. And keep track of which branch is currently trying, because at any moment, at any configuration, you may have more than one choice to go to the next configuration. Then I have to remember which one. So for example, we can label them, right? So there's 1, there's 2, there's 3, and so on. So we gotta remember them. So then a branch that uses big O of f of n space can, if you look at the running time, it could be 2 to the exponential, right? 2 to the big O of length of n. Until the same configuration repeats, right? So because you could have that many unrepeated configurations. When you repeat a configuration, then of course you know that you're running into a loop. But since you're saying that each branch holds, you're not going to run into a repeating configuration. So that's at most this many. Okay, so then, however, at each step, it could be a non-deterministic choice, and you have to remember that choice. So that means that you got to remember this many choices for each branch. So that is non-deterministic space, right? So, so this naive approach doesn't work. However, Savage found a clever way to look at this issue from a different angle. So that's one of the joys they look at this previous wisdom, right? So how you wonder how they could come up with such things. All right, so this is a better approach. The idea is that we could connect space to time. In other words, we could make some kind of connection between space and time. Okay, it's because we do mention time here actually, but we can do a better time connection. So here is this approach. So let's first look at 2 configurations, because in a computation tree of a non-deterministic Turing machine, it moves from one configuration to the next. The only difference is that from a configuration, you may have more than one configurations you could go to. Okay, so now let's just look at C1 and C2 be 2 configurations of the non-deterministic machine, Turing machine, and T a number. So that indicates time, okay, number of steps. Number of steps is time, right? So let T be a time. So then what we want to do is to find out whether we can achieve C2, okay, whether we can go to C2 from C1 within T steps using only big O of f of n space. We should think of that as a big O here. Okay, so put a big O. And this problem is called yieldability problem. So that's what we want to know. So that's how we connect this time, right, to space. So by using this, it makes it possible to look at from a different angle of simulation of a non-deterministic space computation. Okay, using deterministic space computation, but only gain quadratic more time, okay? Quadratically more time. More space, I'm sorry, quadratically more space. Okay, so with C1 being the start configuration and C2 being the accept configuration, and T being the maximum number of steps that the non-deterministic Turing machine can use, okay, then we can determine whether the NTM, the non-deterministic the Turing machine accepts its input recursively. Okay, as follows. So we search for an intermediate configuration, CM. So when we say search for, we can simply guess one, right? We can guess one, or we can search for, and recursively test whether C1 can go to CM within T over 2 steps, and whether CM can go to C2 with T over 2 steps, right? So that breaks it into 2 halves. So in other words, C1 goes to C2 in T steps. We can break it into C1 goes to CM in T over 2 steps. And then from CM, we go to C2 in T over 2 steps. So you combine them, it still is equivalent, right? That equivalent to C1 going to C2 in T steps. So that's what it is. So then we reuse the space for each of the 2 recursive tests, because for each iteration, you can start from over using the space that was used before. We only need to use a space to store the recursion stack of backtracking, because when you do recursion, you have to know where you start. So when you finish computation of the subproblems, you can backtrack to its parent. So we need to remember those, and that we just need extra f of m space to store that configuration. Okay. And the depth of the recursion is log t, okay? Because the number of steps, t is the number of steps. So in this thing, we divide them by half each time. So that means that the depth of this tree is log of t. And we know that t is 2 to the big O of f of n. So that means that the depth is big O of f of n, since you store the returning information using this much space. Then, of course, the total space you would need is the multiplication of these 2. So that's f of n squared. So that is the idea of Savage's theorem, okay, the proof of the Savage's theorem. Okay, now let's see the formal proof here. So we'll write that one up. Let A be a language in n space of f of n, meaning that it is accepted by a non-deterministic Turing machine T in space big O of f of n. So we still need a big O of f of n there. Okay, so now we construct a deterministic Turing machine. Okay, so basically it's to search for intermediate configuration. Well, when you say search, we just think about all possible ones one at a time, and then that becomes deterministic. So that, okay, this deterministic Turing machine M, so that it accepts A in big O of f of n square space by testing if one of T's configuration can yield another within a specific number of steps. So to put things into context, so let W be an input string to T. And let C1 and C2 be configuration of T. And small integer T, now capital T is the machine, small integer T. And then we for this configuration C1 and C2 and an integer t, we define can yield C1, C2, t. That now this is a procedure. We define a program or a procedure that accepts. Okay, so that means that it returns true. If this Turing machine T can go from C1 to C2 in at most T steps along a computation path. If not, can yield outputs reject. So let's see how we can do this. Can yield C1, C2, T. Now remember, it accepts if C1 can go to C2 in T steps. Okay, otherwise it rejects. So we look at, so this is sort of the idea of induction on T. So we start from the base case. So T is either 0 or 1. So these are the cases we consider as the base case. So when T is equal to 0, that means that C1 is equal to C2 because you don't need any step. So this C1 and C2 should be the same. Okay. So if they are the same, then reject, then accept, otherwise reject when T is equal to 0. When T is equal to 1, that means that one step, we should go from C1 to C2. So then we can check it. So we'll accept if T can take a single step from C1 to C2, reject otherwise. When T is greater than 1, then we are going to divide this T by half. Okay, so that means that we'll accept if there is a configuration Cm of T. Okay, such that both can yield C1 Cm in floor T over 2 and can yield Cm to C2 in floor T over 2 accept. Otherwise, reject. So if both of them accept, we accept. Otherwise, if one of them rejects, at least one of them rejects, we reject. Okay, so that is can yield. All right, so now, without loss of generality, we can make T to have a unique accept configuration, C accept. So which means that now, if you think about accept configuration, what we usually mean here is that as long as an accept state is reached and whatever in the tape is considered as an accept configuration. But then there will be too many configurations, too many accept configurations we need to worry about. So of course, we can make it easier. So that means whenever a accept state is reached, this Turing machine will continue on replacing each space used by 0 and move the rewrite head to the very beginning. So then we have a unique accept state. Okay, so then we call that unique accept state C accept. All right, so basically that's what it is. And the start state, of course, you only have one with the input and the initial state at the beginning of the input stream. Next, we're gonna let D be the number of states plus the number of tape symbols on the tape. So that's D is, then you know that the good thing here is that how many configurations do we have? So look at this tape. Okay, so the space here is big O of F of N. And for each of these cells, you can put any of these symbols, and of course the state could be here, could be here, could be here. So that means that I could have at most, so because each of these locations could be a symbol plus a state, and you have this many possible states. So that means that the total number of configurations is bounded above by d to the big O of length of n. So it should have a big O, but since it's a big O is just a constant, so you can just you can just write f of it because that can be easily taken care of. You write big O of f of n, that's fine too. So maybe it should be. So we don't, it would be easier to save some argument there. So that's how many configurations we have. Then T accepts W even only if can yield C star to C accept in this many steps, accepts. Right? So that we know. In addition, we can see that this will take at most big O of f of n square space. This is what we have seen already, because each call to can U requires this much space to store the uncoded CM it chooses, plus space for its recursive calls, which means that you need to remember where it comes back after you finish up the subproblems. Okay, so so we know from the earlier analysis, we know that, so this recursion tree, the depth of it is log d to the big O of, so it's a big O. Okay. So which is simply big O of f of n recursive calls. That means that the total space is big O of f of n squared. Okay. All right, so now there's a one technical detail that we need to take care of in this theorem. Now, most of the proof, it may just end up here, assuming that you know how to compute f of n in space. Right now, this is a value, but we don't know how much space do we need in order to compute it. Right, so that's some technical detail. If you look at Savage's theorem casually, so that detail may be overlooked. So now let's complete this part. So fill this hole. So this means that, okay, we know f of n represents a space, but this is a value. So to compute this value, I don't know how much space do I need. If that space I need is more than this, then I cannot just say, okay, I'm going to compute this, because you already need more space than just computing these things. So that means now I have two issues here. One issue is computing f of n can just be using the same amount of space or with proportional amount of space, right? So then we have a concept called space honest. So if f of n is space honest, meaning if it is computable with big O of f of n space, then we can compute d to the f of n before the first call to can U, so then everything follows. So that's the easy case. However, if f of n is not space honest, computing f of n may need more space, then we cannot do this computation directly. Instead, we are going to use the following methods. Okay, so this method is to add a size parameter s to can u. Instead of computing f of n directly, I'm going to list all possible values, okay, without really computing f of n. Right? So that is the trick here. Okay, so we can add a size parameter and only iterate over configurations, which uses at most S space. Okay, so now we let C accept comma S be the configuration of T. It's non-deterministic Turing machine. That is the accept state followed by S zeros. So that means we only use S space. Okay, so that's what it means. We only use S space. So we model T using the following algorithm without computing f of n. Because we don't know what f of n is, I'm going to try all possible values. So I from 1 to blah, 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 I don't know when it's going to stop. Okay, so the stopping will be depending on the following. So for each configuration CG with length less than I plus 1, okay, if can u C1 CG, okay, that means I can go from C1 to CG in d to the I plus 1 steps in I plus 1 space, within I plus 1 space, right? So this is a step, this is space. See, this is how we make connection of time and space here. So very clever, okay? So if we can go to CG from C1 in d to the I plus 1 space, now this is deterministic space, deterministic time in within I plus 1 space. Okay, so if this is true, then we accept if this CG is actually equal to C accept comma I plus 1, again using I plus 1 space. And then we increment I and loop. Okay, so if at some point this is not going to be true, then we reject. So why it works? So a simple argument, then we can be convinced that it actually works. So this algorithm accepts if at any time can u tells us we can reach an accept state. In addition, it rejects if we reach an I such that I cannot u any configuration of length I plus 1. ST never uses more than f of n space. We will thus reject once I reaches f of n plus 1, right? So this is a clever connection here, because by assumption, T does not use more than f of n steps. So that means that if your I will ever reach this point, that means that this can u fails for all the space you have tried. So the space within f of n you can try. So that means that then we reject. Okay, so this is a very clever touch, sort of like a brilliant observation or brilliant stroke, right? So if you want to put that way, that makes this work finally. Okay, if you are into these things, you can enjoy it very much. It's really clever, right? So by reading a clever proof made by early people, you sort of like you talk to a genius, right? So you learn and you enjoy, you appreciate. So the last slide is simple. It just defines classes. So we define PSPACE. So P represents polynomial space. So that means that it is the union of space of n to the k from 1 to infinity. So that's PSPACE. So from space complexity point of view, we know that PSPACE is equal to n space, because n space is also this n space n to the k, but we know n space of n to the k is included in space of n to the 2k, so that is included in PSPACE. So that means that these two classes are actually identical. Space, PSPACE is equal to NP space. And then we define exponential time, so which is a union of deterministic time of 2 to the n k, k from 0 to infinity. So then we know that NP space is included in exp time. So finally, we have this sort of pretty well, except this part, right? So the middle part is Savage's theorem. The other part is kind of trivial or straightforward. So this is directly from Savage's theorem. The other part, this is directly from definition. And this is not hard to do. And NP, of course, is in PSPACE, because the number of time you use is bounded. So you just convert those time to space, then it still be bounded. So that part is straightforward. Okay, so now that is this part of the video. So we look at Savage's theorem that says deterministic space and non-deterministic space, they are equal within quadratic function. And hence PSPACE is equal to NP space. That is a theorem that we don't have for deterministic time versus non-deterministic time. We don't have yet, so we don't know what's going to be. Okay, so let's look at, let's open up. What time is it? Okay. So we have some time left, so we are going to look at the next slide. So are there any questions for me at this time? Okay, then. Let's here. And we look at space complete problems. P-space completeness. Okay, so the definition is similar to NP completeness. So we use this polynomial time reduction. So a language B is P-space complete if it satisfies two conditions. Number one, B is in P-space. And number two, every A in P-space is polynomial time reducible to B. Okay, so this is sort of similar to NP completeness. Then if B merely satisfies conditions 2, then we say that it is P-space hard. Okay, so that concept is pretty straightforward once we understand NP completeness. However, then the next issue is we know that we need to see whether whether P-space complete problems exist. Okay, so we're going to show that it is NP complete to determine whether a fully quantified Boolean formula is true. Okay, so now let's do some comments here. So let me start a whiteboard. Okay, so when we first look at Boolean formula, in connection to satisfiability, okay, so what we implicitly mean, so this is for SAT, we explicitly mean that there exists x1, x2 to xn such that this formula is true. That's satisfiability. So there, when we say there is a truth assignment, it really means there is one. But since we don't have any, so this is called existential quantifier. And the other one is universal quantifier. That means for or. We only have one, so we don't have to write it. So that's why we say it's implicit. But then if you add for or, so you have existential. So this so basically it just means that we don't need this. That means that as long as there is a truth assignment to make it true. But then if every variable here, I could either have an existential quantifier or a universal quantifier to bound them. Now remember, when we have for or, it means for all truth assignments for that particular variable or a set of variables, right? So for instance, for x1, x2, it means that we have to look at all possible truth assignments for x1 and x2. That is 0, 0, 0, 1, 1, 0, 1, 1. So we got to look at all of them. So that's much different from there exists a truth assignment. That means any one of them, if it is true, then it works. Here I have to check for all possible truth assignments for these two variables because I have a universal quantifier. This formula should also be true, then I can say that formula is true. So now we are going to look at fully quantified Boolean formula with two quantifiers, existential and universal. Then this problem becomes PSPACE complete. So if you imagine without this quantifier, it's NP complete, and with these quantifiers, it's reasonable to think that it is PSPACE complete, right? So as a matter of fact, it is. Okay, so let's go back to our slide. Doesn't show. Sometimes I don't know how. Share. Let's see if it shows up. Okay, shows up. All right. So where were we? So we're here. We were here. So we'll show that it is PSPACE complete. So this should be PSPACE. Okay, in terms of MP, we know MP is not fully quantified. All right, so when each variable of a formula appears within the scope of some quantifier, either an existential quantifier or a universal quantifier, the formula is said to be fully quantified. A fully quantified Boolean formula is sometimes called a sentence and is always either true or false. Okay, so this sentence means that it cannot be both, right? So for instance, when we look at Boolean formula for SAT, so for some truth assignment, it could be true, and for some other, it could be false. But since it's fully quantified in our case, then it is always either true or false. It cannot be, for some it is true, for some other it's false. For example, this formula for all x, there exists y such that x or y and x bar or y bar is fully quantified because you have two variables and then you have x and y. However, if the quantifier for all x is removed from this formula, then it is no longer fully quantified, which is neither true nor false. It just says there exists y and this X, okay, you have no, it's not quantified. So that means that it is not a sentence. Okay. So now let's define TQBF. To be a set of formula. So this is encoding of a formula phi. Phi is fully quantified Boolean formula, and it is true. So this T here represents true, fully quantified Boolean formula. Okay, then TQBF is PSPACE complete. Okay. All right, so now let's pause a little bit and try to think about what we are trying to do here. So what we are trying to do is to the following two things, right? One, we want to show TQBF is in PSPACE. The second, for any problem in PSPACE, that problem can be polynomial time, many one reducible, or can be reduced in polynomial time to TQBF. So let's bring up a whiteboard here. Will that work? Yeah. Okay. So we define TQBF. That represents true, fully bounded, quantified Boolean formula. And we want to show it is NP complete, so we want to show two things. One is it is in PSPACE. Okay, the other is that for any A in PSPACE. So that means that there is a deterministic Turing machine that accepts A in polynomial space. We have that A is for some reason the server is slow, so the response handwriting doesn't show up as fast as we would hope to see it happen. So for A in PSPACE, we have A is reducible, is many one reducible in polynomial time to TQBF. So this just means that A can be accepted by a deterministic Turing machine in PSPACE. So we want to do these two things. So this is one to show. One to show these two things. Okay, so now at least we know the logic here. Then when we look at the proof, so we always try to think about what we need to do. Then we will have a better time understanding it. Okay, so that's the first thing. We want to show that TQBF doesn't, for some reason, doesn't show. All right. Okay. So for this purpose, we want to construct a deterministic Turing machine T to accept this. So for any formula, right, as input. So this is a fully quantified Boolean formula, which is an instance of TQBF. Of course, we don't know whether it's true or false. So we want this Turing machine we construct to determine whether it is true or false. Remember, only one can happen, right? So number one, we check. So this T checks if this formula phi contains no quantifiers, then it is an expression with only constants. So evaluate phi and accept it if it is true, otherwise reject. Because we're assuming it has to be fully quantified. So that means if it contains variables, there must be quantifiers for that variable. If there is no quantifier, that means the formula is just a constant, so no formulas, okay? So then it's easy to evaluate using the Morgan's law and then see whether that constant returns true or false. That's easy. And next, we're going to say that if phi equals there exists x, another formula psi, then we recursively call T on psi, first with 0 substituted for x, and then with 1 substituted for x. So because this x can only be either 1 or 0. If either results is accept, then accept, otherwise reject. So that's for existential quantifier. Okay, if phi equals for all x psi, so this is universal quantifier, then we recursively call T on psi. First with 0 substituted for x, and then 1 substituted for x, right? Because x could be either 0 or 1. So we consider both of them. If both of them accept, then we accept, otherwise reject. So that's straightforward. So the space it needs is to just evaluate this formula. So that means it's still, actually it's a linear space. Okay, so then this TQBF is in P space. This T is deterministic. Okay, so that first part is straightforward. Now let's look at the second part. Okay, so now we let A be a language decided by a deterministic Turing machine M in space n to the k for some constant k. So let me put T here. Okay. Now we're going to construct a polynomial time reduction from A to TQBF. The construction here is actually similar to Savage's theorem. Okay, so the reduction maps a string W to a quantified Boolean formula phi, and that is true if and only if M accepts W. So that's what we want this reduction to be. All right, so now from any computation or from any from this M, we're going to construct a formula to represent a computation. Okay, so a computation would be from a initial configuration to the accept configuration. So that's what we are going to do. So now let C1 and C2 represent two configurations, and let T represent a number of steps that C1 can reach C2 in T steps. And then we construct a formula phi sub C1 and C2 and T, indicate that this formula represents that that path of configurations. So if we assign C1 and C2 to actual configurations, the formula is true if and only if M can go from C1 to C2 in at most T steps. So then, of course, if we replace C1 with C start and C2 with C accept, and H is 2 to the D of f of n for some D, that's a constant because space, right? So as we said earlier, if you have space f of n, then the total number of different configurations is at most some constant to the f of n. Then you take a log, I'm sorry, you change it to a base 2, right? So for any C of f of n, so that's how many different configurations we have. Then you take, so that's to change the base C to 2, so that is equal to log. It doesn't show up here. C to the f of n, so that is really equal to 2 to the f of n times log c. So you write log c to be d, then you get this. H is 2 to the d of f of n, d times f of n for a constant d. Okay, so that's how many different configurations we could have. Then for convenience, because we want to divide this t by 2 each time. So instead of using floor, we're going to just assume that t is a power of 2. Otherwise, you have to use a floor notation. Okay, so in particular, we construct a formula to encode the contents of configuration cells. Okay, so each cell has several variables associated with it, one for each tape symbol and state. So in other words, we are using, as before, when we reduce boundary tiling to SAT, so we use Boolean formula to represent tiling, but that tiling really, if you do a step backward, that tiling represents legal computation of a Turing machine. So that's what we do here. So we use a fully quantified Boolean formula to represent a computation. So each configuration here uses n to the k cells, and hence is encoded by this many variables, big O of n to the k, because you need to represent the number of cells, and you need to represent the state, the head locations and the states. So the number of variables is at most the big O of n to the k many. All right. So looks like I will not have time to finish up this proof. So I think it's better that I stop here. And then we'll continue. We'll finish this proof next time. Okay, so we are on page 5 because there is enough time to finish up, right? So, okay, so I'm gonna stop here, and I have few minutes for Q&A. Are there any questions for me? I hope that you are still with me, more or less. An evening class, 3 hours straight, could be tiring. All right. Okay, then I'm going to stop here, and I'm going to finish up this proof next time.